We're going to talk about probability and also the standard distribution. We'll start with probability first. This should coincide right along with your Chapter 5 PowerPoint and basically should cover through approximately PowerPoint slide 16 in today's little doodlecast video. So starting with probability, just to define it overall, probability is the likelihood an event will occur. Now when we talk about probability, we're looking at prediction. So there is actually an equation for it as well as a notation. So when we look at probability, it's P is the notation, and we'll say probability of X equals f of x over n. Now, P, this here, is our notation. But this is just basically an equation showing you how we would come up with probability. X is a score, or what you are looking to predict. So this here, f of x, is the frequency that that score occurs within the sample, and n is your sample size. So if we consider probability in this sense, think about if you have a die. Okay, so we're going to look at, we're going to go to a new page. Let's say we have our lovely die here. It's pretty sloppy, but we'll say it's nice artist work, okay? And we know here's 1, here's the 2 dots, here's the 3 dots, okay? So we have a die, okay? Let's take into consideration our equation again. P of x equals f of x over n, okay? Now let's assume we want to see what the probability is of rolling a 1 with a die. So if we look at this die, we're just looking at this side. Now it's easy with a die because there's, just one side for each number. So let's take that into account. Our x, so we have P, and we're looking for 1. Whoops, let's erase that. We're specifically looking for 1 equals the frequency of 1. 1 only occurs one time, right? Only once. Over, and a die has 6 sides, 6, right? So we come up with a fraction. 1 over 6 is our probability. But it's very important that you understand in statistics, we don't report anything in fractions. We always report it in decimal. So our final answer for this in particular is P equals 0.1666, it's repeating, which actually equals 0.17. That's our final answer. So it's telling us that we have a probability of 0.17 to roll a 1 with 1 die. It's as simple as that. We just need to find that sample size and find how many times our score or value of interest occurs within that sample. And then we can find the probability. And that's the most basic, simplest form of probability. And probability is going to be used throughout statistics in a much more complex way, but this is the most basic form, is just the probability of something occurring, or the likelihood of something occurring. So with that being said, let's look at some of the rules about probability that's important to understand. So we'll call them P rules, is what we're going to call them. The first rule is that probability will always vary between 0 and 1. So vary between sorry about the sloppiness, 0 and 1. Okay, so if we have a 0 probability, that means we have no likelihood of something occurring. If we have 1, that means we have a high likelihood. And if we think about probability, it is also reported as a decimal or percentage. So it could be p equals 1.00, which means the same thing basically as p equals 1, or probability is 100%, not p equals. So 1 is 100%, whereas 0 is 0%. We'll kind of throw that in there. So no likelihood to 100% likely. So it's only between 0 and 1. So that leads us right to our next rule, which is that it can never be negative. It cannot. It doesn't make sense to have a negative 50% or a negative 100%. So therefore, it wouldn't be appropriate for us to say a p equals negative 0.50 or p equals negative 1.00. So it's never negative. It's either probable, which is greater than 0, or it's not probable, which means it's equal to 0. So this is going to be important theoretically throughout the semester for what we're going to be doing, because most everything that we do is based on probability. So we'll look at the transition into normal distributions, because normal distributions are often composed of probabilities, or what we call proportions, which are equivalent to probability. So we know that normal distribution, if you remember, we've been looking at them, are these theoretical distributions. We basically utilize the normal distribution as a theoretical distribution. This is kind of like the ideal distribution, and we compare everything to it. Most of our behavioral research approximates a normal distribution. Where, remember, the normal distribution, it's symmetrical, the mean, median, and mode all kind of pile up right in the middle. You have tails on both sides. So is what we're doing with the normal distribution is we're using this to compare all of our other samples and distributions to. That's why it's called a theoretical distribution. So these scores in a normal distribution that kind of fall in this area, see this large area here, these are close to average. So these are more likely to happen. These are what we would call, what we would consider likely to occur, whereas these and the areas out here, these would be unlikely. So rare, even here and here in the tails. So when we look at the normal distribution, we can see the majority of scores pile in the middle, and then everything kind of tapers off at the ends where things do not occur quite as often. So there's some things about the normal distribution that are important to understand. So there are basically 8 characteristics. It says 6, but that's wrong. There's actually 8 characteristics that you need to know about the normal distribution. The first characteristic is that it's mathematically defined. And we'll just put math defined. You don't need to know the math that defines that shape of the normal distribution based on the x and y axis, but know that there is a mathematical definition for it, and that's how it's calculated. So when you're working with SPSS, that's what SPSS is doing. It's creating a theoretical normal distribution to compare things to through mathematical definitions. So that kind of flows into that second characteristic that, of course, we talked about this. It's theoretical, that second characteristic. We use this ideal distribution to compare everything to, because behavioral data, social behavioral sciences, the data approximates a normal distribution typically. So we can easily compare it to this theoretical normal distribution, and it makes those comparisons nice and smooth, and we can start seeing, is something different? Is it the same? Is it unlikely to occur or likely to occur? The third is that the central tendencies are all located at the 50th percentile. So the mean, median, and mode are all located at the 50th percentile. Now, if you look at the distribution, if you're truly dealing with a symmetrical distribution, that theoretical normal distribution, you should know that it's equal on both sides. So right down the middle is the mean, median, and mode, and then half of the data is on this side, 50% is on this side, 50% is on this side. In every normal distribution, it is like that, which could also be said as P equals 0.50, or here, P equals 0.50, because probability and proportion are equivalent. Basically, they mean the same thing, probability and proportion, and they are equivalent to percentage. You convert a probability or proportion to percentage by moving the decimal over 2 places to the right. If you look, this total distribution, you add all this up, it's 100% if you add both sides together. So 50% is on the high side, 50% is on the low side. That is common in every distribution. If you think about that, this right into our fourth characteristics, which is saying that a normal distribution is symmetrical. So it's equal on both sides. 50% on one side, 50% on the other side. So the amount of data is exactly the same below the mean as it is above the mean. And you can always tell this by using the folding test. Basically take your distribution and fold it in half. Our fifth characteristic is that the mean can equal any value. Any value. It doesn't matter. The mean can be basically all the way negative infinity to positive infinity. So it can equal a negative number, it can equal a positive number, it doesn't matter. Think about if we were measuring the amount of weight loss in diet patients. If we're talking about weight loss, we're talking about negative numbers. So the mean could be a negative number easily, or it could be positive. The mean can be any value. It doesn't matter. Within a normal distribution, if you're comparing to using that as a theoretical distribution, you basically replace the mean of that theoretical distribution with any mean for any data set that you have. Our sixth characteristic, which is important, the standard deviation. Now we know the mean can be positive or negative, right? But the standard deviation can never be negative. Never be negative. This is important to understand. Is what it's talking about is that data either varies or it doesn't. It can't vary by a negative amount. It either varies or it doesn't. So standard deviation is basically greater than or equal to 0. It is never, ever negative. And that is key to understanding. So the standard deviation is just talking about how much scores vary around a mean. We kind of touched base on this, but the total proportion in a distribution is equal to 1.00. So I'm going to actually, we're going to erase that because we're going to, if I can erase it, because we're going to actually use a different page. We're going to need a different page for this one. Look at number 7. So we're going to look at this distribution. So when they say the total proportion under the curve, they're just talking about the entire distribution, basically. All of this is equal to p equals 1.00, which is 100%, is what it is. This entire area is 100%. So you can use proportions of the area to segregate it, like we did before, 50% here, 50% here, but the total amount under the curve is 100%. And then last, as far as characteristics, the 8th characteristic is the tails of a normal distribution are asymptotic. So asymptotic is the key word. So if you'll notice in the distributions I draw here and here, the tails never touch. They don't. In a normal distribution, they just continue on for infinity. They approach the x-axis, so you'll see them getting closer and closer, but they never actually touch. That is because it's allowing for a possibility of outliers. We're allowing for any kind of extreme scores to fall out there. So you're never going to see them touch. So that's the last characteristic, is that it is an asymptotic distribution. So those tails never touch. So when we look at the normal distribution, we'll kind of look at a drawing of it. If you'll note in your textbook or on the PowerPoint, it's split up into sections. And when we talk about standard deviation, we are talking about how much things deviate from the mean. So whatever the mean is here, there's these segments. In every normal distribution, there's, a positive 1 here for 1 standard deviation above the mean. There's a positive 2 here for 2 standard deviations above the mean. There's a negative 1 here for negative 1 standard deviation above the mean. And a negative 2, and then there's a negative 3 and a positive 3. And what it is it's the same in every single distribution. And the proportions are equivalent, and all the proportions add up to be 100%. So then we can easily kind of utilize the normal distribution to state whether something is normal or abnormal, like whether behavior is normal or abnormal. If we look at, we can basically say, anything, within a certain range, we consider that normal, right? So this is the average. But anything out here, this would be what we would consider abnormal, just like that likely. So it's likely to occur in that middle. It's unlikely for it to occur out in the far tails. That's where we can get into later that inferential statistics and start talking about whether something is significantly different, which is basically like saying abnormal. That is, if it's falling way out into the tails. So we can utilize the information of the standard normal distribution and where things fall based on standard deviations, even in greater detail when we look at the standard normal distribution known as the standard distribution. So in this case, I'll call it the standard normal, or I'll put standardized. It's used interchangeably. So standardized distribution is what that is it's this normal distribution, and it's been standardized so that any mean in the middle is equivalent to 0. So in a standard normal distribution, the mean equals 0, and the standard deviation of the standard normal distribution equals 1. So then we have our 1, our 2, our negative 1, negative 1, negative 2. So it doesn't matter, everything has been standardized, but these are what are called, it doesn't matter what in the original data is what I mean, the mean and standard deviation are, because it's going to be transitioned to the standard distribution, standard normal distribution, where we are now using what are called Z-scores. These are Z-scores. So whatever standard deviation there was in the original data set, it has a Z-score for every value within that. Every single value has its own Z-score. So if you have let's say on the exam, let's say exam 1, we have a 75% average in the class. If you actually obtained a 75% and the class average was 75%, your Z-score would be 0. Z equals 0 is what that is. And so is what happens, looking at Z-scores a little bit differently. We can see Z-scores used to represent values or typical scores in the distribution. So Z-scores identify the location of every score in a distribution. Okay? And that's in a standardized distribution. So basically a Z-score with a Z equals -1 says it's below the mean. A Z-score of +1, so this is below mean. A Z-score which equals +1 is above the mean. So a Z-score tells us, the sign basically tells us where a score is located, either above or below the mean. And whereas the value or the number, we'll say the number of the Z-score, we'll put here Z-score so you understand what's going on. The number tells us the distance in standard units. So if you think about this, let's take a look at a common population distribution that multiple times. I've used IQ scores many times. So here we have our distribution, and I said the average IQ is 100. That's right in the middle, that mean. Well, if you look at the population information parameters, we know our standard deviation of IQ scores specifically equals 15. So with that being said, we will know where things are located. So right here is 1 standard deviation above the mean. Here is 2 standard deviations above the mean. So we know that the score here at the 1 standard deviation above is 115. Because there's 15 points, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15 points between the mean and one standard deviation. For every standard deviation, there's 15 points. So I'll put here points. So if I said you fell one standard deviation above the mean, your z-score would be equal to 1.00, and a positive specifically. It's important that we keep our signs accurate because it's a big difference. If you fell here, your your raw score would be 85 because it's 15 points below and you'd be one standard deviation below. Well, here your z equals negative 1.00, saying you're one standard deviation below the mean. So this is going to be important in understanding within a few weeks, especially, because we're going to start looking at finding specific z-scores or raw scores, depending. And we're going to be using a standard normal distribution, or we could use the standard normal transformation equation. So that standard normal transformation equation is z equals, and this I'm going to give you the population one first. A little crooked. Z equals x minus mu over standard deviation. Now, remember, it's important to start knowing your notations. This is a mean, and it's specifically for our population. Here is our standard deviation, right? For a population. Once again, population. So that means we need to know, how do we calculate those things? How do we get those? Well, you should be easily able to get the mean. It doesn't change between population and sample. But guess what? Our standard deviation for the population is calculated differently than it is for a sample. Remember, sums a square divided by n, sample size. So it's important to know the difference. This is what we're going to use to find a z. So specifically, maybe we have a specific score and we want to find out what that z-score location is. This is what we'll use. So let's look at sample. For our sample, standard normal transformation equation, or z-score equation, is z equals x minus m over standard deviation. Now again, we have to be careful. We have a mean, specifically for the sample. We have a standard deviation, right? Specifically for that sample again. And if you recall, our equation changes up a little bit. So we have standard deviation equals sums a square over n minus 1. Take the square root of all that. It changes it up. And that again is if we would want to find x, so a value or a raw score, specifically within a distribution. So let's do a little practice one. So let's assume, okay, we have a distribution, and let's say it's exam scores, a normal distribution, and it's a sample. Our sample mean equals 75, okay, and let's say our standard deviation equals 12, okay. And let's assume that on the exam you got an 80%. Okay? Where would our z-score be for 80%? Is what we would need to do is plug it in to our transformation equation, x minus m over standard deviation. So we end up having 80, we're going to go z equals 80 minus 75 divided by 12. Now when you're calculating something like this, be sure that you're using parentheses around that numerator, so around the 80 and the 75. Otherwise you could end up with 12 being divided into 75 instead of the difference between those. So you should be getting a z-score of positive 0.42 basically. I got 0.41666, so it's rounded to 0.42. It's important that you're putting your numerator in the right order because that's going to tell us whether it's positive. It wouldn't make sense if you came up with a negative 0.42, would it? If this was a negative, that would be a problem because 80% is higher than 75. So you know that your score falls over here somewhere. You know it's going to be above the mean. So you know your z-score should be positive, not negative. And that's one way to verify, is just kind of go back and check. Does this make sense? Is this score higher than the mean or lower than the mean? If it's higher, the z-score should be positive. If it's lower than the mean, your z-score should be negative. So that wraps up this Doodlecast video for now. What I'd like you to do is go into that Canvas week 5 hybrid and answer those questions and come up with some questions that you may have for class. And we will finish lecturing on Chapter 5 on the next class period. Thank you.